The Cerrejón open-pit coal mine in modern Colombia is a harsh, industrial landscape, defined by massive machinery and constant rock dust. Paleontologists initially arrived here to hunt for fossilized plants. They were looking for evidence of ancient leaves and branches trapped within the coal seams. But as they excavated, they discovered something that didn't belong to a plant: enormous, fossilized vertebrae embedded directly in the rock. This chart shows the scale of the find. Left is the vertebrae of a modern anaconda, one of Earth's largest snakes. Right is the fossil. Based on that bone, researchers mapped a predator 42 feet long, weighing 2,500 pounds. Reptiles rely on their surrounding environment for body heat, but an animal of this sheer mass is too thick for solar warmth to penetrate deep into its tissue. At today's equatorial temperatures, a 2,500-pound snake would freeze from the inside out. The existence of this fossil proved that either our working knowledge of biology was missing a piece, or the history of Earth's climate was radically different than we realized. To find the answer, scientists looked at the rules of poikilothermy, the biological system that governs cold-blooded animals. Unlike mammals, poikilotherms absorb external thermal energy to fuel their muscles. Thus, as a reptile's size increases, its environment's temperature must rise proportionally. If the animal grows too large, external heat cannot reach its center and internal systems fail. Researchers realized this biological constraint offered a specific advantage. It meant Titanoboa wasn't just a massive predator, but a perfectly calibrated fossilized thermometer. Scientists took the snake's 2,500-pound mass and ran the metabolic math in reverse. The firm conclusion: to support a creature this scale, the ancient equator had to average over 90 degrees Fahrenheit year-round. That is a significant departure from the modern tropics, which today average about 10 degrees cooler. By treating the snake's anatomy as a thermal data point, scientists mapped a previously unknown, radically hotter epoch in Earth's history. This intense heat fueled the growth of the Earth's first recorded neotropical rainforest. It was a world of bizarre, scaled-up giants. The heat supported massive crocodilians and turtles the size of cars, all thriving in a hyper-warm ecosystem. In this environment, Titanoboa was the absolute apex predator, physically dominant and perfectly adapted to its high-temperature habitat. But the habitat changed. Over millions of years, the global climate began a gradual cooling shift. As the temperatures dropped, the metabolic scaling law turned against the giants. The environment no longer provided the energy supply required to keep such massive bodies functioning. Unable to maintain its core temperature, Titanoboa went extinct, leaving the forests to smaller, more efficient reptiles and mammals. This ancient extinction provides a vital case study for contemporary climate scientists. It offers empirical proof that tropical rainforests can not only survive, but generate massive biodiversity under extreme greenhouse warming. As our own planet warms, this impossible monster serves as a scientific baseline, helping us predict how life might adapt to a hotter future.